Swayam Prabha. Digital India. Educated India.
Hello, students. Now that we have familiarized ourselves with basic concepts of probability distribution functions and probability mass functions, it's time to move to next level of uh, concepts which would be covered in this Bayesian approach. Uh, so some of the discussions that we will have in this particular section may be bit involving in terms of mathematics. However, I would urge you to focus on the concept, why Bayesian framework is needed, in what situation Bayesian approaches are useful over frequentist approaches. Frequentist approaches are those approaches that are solely data driven without accounting for any prior information, and how we can make use of limited data by using Bayesian approach. Wherever mathematics will come, I'll try to do end-to-end derivation. However, this is not a course on probability and statistics only. So it is important to understand essence, that how a particular mathematics is following. But for completeness, all these derivations would be done in entirety as they should be done in a typical probability and statistics setup. In this particular module, we are going to have a gentle introduction to Bayesian approach, distinguish Bayesian approach from classical approach, and then we will talk about how evidence and prior are brought together. Then we will talk about Bayesian theorem. You might be familiar with Bayes theorem from your high school or senior secondary school, but we will put it into engineering context. And later on, when we will go to decision making problem, we will use Bayesian approach many times as and when prior and evidence is available to us. Then we will use Bayesian theorem or Bayesian approach to do parameter estimation, which is fundamental to statistics, probability, and decision making as well. That given data, how you would estimate parameters. And then we will conclude this particular module with our example on flood. As you may remember that we have been following a typical flood example and trying to solve it using multiple ways, methods, and we will also do that how we can actually use Bayesian approach in a real world setup. So, if you remember, in our earlier modules, we spoke about two kinds of uncertainty. One was aleatoric and one was epistemic. So, aleatoric uncertainty is essentially part inherent to any data collection process, any sampling process that we do in world of science and engineering, and that is what we try to characterize. We also call aleatoric uncertainty as irreducible uncertainty. So we try to characterize it, and one way to characterize aleatoric uncertainty is to get the estimates of probability distribution functions or probability mass function. So we can say that aleatoric uncertainty gives rise to probability distribution functions. Then another type of uncertainty that we spoke about was epistemic uncertainty, which originates from lack of confidence in probability distribution. Why we will have lack of confidence in probability distribution? If our understanding or knowledge about system or phenomena is limited, and hence our models will also reflect that limited understanding, and that would give rise to epistemic uncertainty. The outcome of this lack of confidence is reflected in that we will have limited confidence in the resulting PDFs also. Now, we have to always deal with these two sources of uncertainty in any probability statistics or decision making framework. Uh, I'm using probability statistics and decision making in one line because all of these are components of any risk assessment framework. Uh, and this is where Bayesian approach helps us in multiple ways. So, first way in which Bayesian approach can help us is to systematically update the existing aleatory and epistemic uncertainties. For example, you went to a site, you saw that there are some data archives available there, but that particular data is only available for 5 years. Using that particular data, you will do some statistics, estimate mean, estimate standard deviation, and so on, and make some inference about a particular phenomena under investigation. Let us say in this case, that is floods. Now, you have set up a monitoring station there, and more data is coming into picture. That is, now gauge is working for next 5 years, 10 years, 15 years, 20 years. So you are collecting more and more evidence for that particular observation. Now you need a way to incorporate that, update the information that you are getting with the prior information that was already available at that particular place. And the same thing applies to epistemic uncertainty. For example, you have built some model, you have drawn some inference about the system using that model, and you understand that this particular model has a lot of limitations. But as the time passes, as our understanding improves, you come up with next generation of models. Now there are two ways. You can keep on starting this particular exercise of drawing inference from scratch, or find a way to add or incorporate new information as and when it is available into the existing data sets. And this is where Bayesian approaches come into picture to help you update already existing information with the new information that is being generated. And you can already sense that how powerful this approach can be when data is being generated continuously, or we are doing some sort of active data collection or training model actively. That is, as and when new sample is available, it should become part of the sample space and parameters should be updated. Another way is that it provides an alternative basis of combining these two types of uncertainty. So, for example, although we talk about epistemic and aleatoric uncertainty as if they are completely distinguishable, they can be totally separated, but that does not happen in real world. Most of the times, these two uncertainties are overlapping, sometimes hard to separate from each other, or in fact they may have significant overlap in a sense that you have some information about the system with high confidence, some information with the low confidence, and that's where that these uncertainties come together. And Bayesian approach gives us an interesting way to combine these two uncertainties together. And very importantly, third use of Bayesian approach is to estimate parameters for underlying probability distribution. When we spoke about normal distribution, it was two parameter distribution. We only had to estimate mean and sigma. Then we spoke about other distributions like Poisson process, Poisson distribution, where we have to estimate lambda. But these distributions, as long as they follow all the rules that need to be followed by any probability distribution, may have parameters that we are not familiar of, that what would be the exact functional form or what would be the exact derivation of these parameters. So we have to give the mathematical treatment to estimate these particular parameters, and that's where Bayesian approach also comes into picture. While estimating parameters using true Bayesian approach, that is using posterior, I'll talk about these keywords, become quite mathematically involving, but Bayesian thinking does help us articulate that parameter estimation in much better way, and we will try to do all these things with help of an example. Again, as I said that there is no free lunch theorem in sciences and engineering. Same is with Bayesian approach. While it is very, very powerful, it is mathematically very much involving, and sometimes the mathematical forms that we get, they become intractable, that you cannot solve them analytically. That's why we have to be always cautious that where to use classical approach or Bayesian approach. But again, if you have really limited data size, sample size, or actively parameters have to be obtained, or uncertainties have to be combined, Bayesian approach is the way to go. Now, since we are talking about Bayesian approach, where to use it, let's talk about limitation of classical approach. Classical approach, as I mentioned, is purely data driven. So we need lot of data. If you have to estimate mean or variance, for example, you would need large amount of data, at least a few hundreds of sample, although statistically speaking you need to have minimum of 30 samples anecdotally speaking to estimate mean and variance. But to have robust estimates of mean and variance, it's expected that you would have large volume of data to draw inferences about parameters or phenomena when you are using purely data driven approach or purely classical approach. Also, when observations are limited, there is no way to incorporate experience into decision making in classical approach. For example, you went to a site, you are monitoring flood situation there, you just believe the gauge, you got the data from the gauge. It may happen that that particular gauge may be off or not working for some period of time, or it might have happened that somebody has moved that gauge from one place to another place and you have no information reflected in that particular data sheet. But then a person who has been living at that particular place for last decades come to you and tell you, hey, that this particular place got a serious flooding 5 years ago, 10 years ago. That means that field experience is coming into picture. But if you are using a classical approach, you would be just going ahead with the data, and there is no way to incorporate that field knowledge or field information that is coming your way. And that is one big limitation of classical approach, that there is no scope of updation of some judgmental information that you have or some experience that somebody is bringing to you about that particular system. So again, reiterating what this classical approach is, whatever we have done up before this module, they were classic example of classical approach. Again, a quick revision that how we estimated parameter using classical approach, that we observed flood for 15 years, and number of years, we observed total number of floods to be 15, and 30 was the number of years in which observation was made. We estimated lambda as how many floods are expected per year. We can simply say 15 divided by 30, 0.5 floods per year. Even in this simple example, you have to make observation over 30 years of time, and collecting observation is an expensive process. It's a costly process. Moreover, even if you have all the monetary resources or otherwise resources available to us, you cannot go back in past and put the gauges there. So sometimes even if you have resources today, history of data collection has already been lost. So you would not be able to estimate those particular parameters if historical data is not available for long period of time. And that is one pinpointed limitation of these classical approaches. Uh, we have been talking about normal distribution a lot, and I will be using these particular parameters again and again. That's why, again, re-emphasizing the fact that we already saw it in case of lambda. And now if you talk about estimating mean and variance using classical approach, let us say that over 5 years we observed these flood depths at a given place: 4.5, 5.1, 5.3, 4.8, 5. Now you have just observed the data, you only want to use classical approach, and I ask you to calculate mean and variance. It's straightforward. You can calculate sample mean. Remember, this is not the population mean, this is the sample mean. Population may have hundreds of years, but you are just observing sample. So sample mean is subset of population mean. But we are trying to draw the inference about population mean by looking at the sample, right? So wherever I will be representing this X bar, I will be talking about sample mean. So sample mean in this case comes out to be 4.94 feet. This is the best guess I can take about average of population just by looking at these particular samples. Similarly, if I talk about standard deviation, it is 1 upon n minus 1. In this particular module, we will also talk about why n minus 1. Why not 1 by n? That is also sample variance, because it is being computed on sample and focus on this n minus 1, that it is not 1 by n but 1 upon n minus 1, because we are talking about sample variance. But if you have to calculate population variance, it would be still be 1 by n x minus x bar square, and here it comes out to be 0.3138 just by plugging in these particular values here. And interestingly, it's not necessary at all that sample variance would be equal to sample population variance. They may be different from each other depending upon how many samples you have, and uh, and what is quality of data and so on. So it is, these two words are not interchangeable. Also, it may coincidentally happen that sample variance turns out to be very close to or equal to population variance if you have large volume of data. But this is one mistake that students typically do whenever we talk about these sample variances and population variances. Whatever you observe, that is based on sample, and hence sample mean and sample variance. Now, question arises how we will incorporate this prior information into our Bayesian framework. As we said that, Bayesian approach gives us way to combine prior data with observational data. Prior knowledge is expressed as prior distribution. It's all playing with distributions, multiplying them and so on, but ultimately prior knowledge is encapsulated in a mathematical form, and we will often refer to that as a prior distribution. We may have an informed prior where prior is really having a lot of information, or we may have a flat prior or a diffused prior where prior does not convey anything meaningful or just talks about all possibilities happening uniformly. Even in that case, prior may still help you restrict the domain of information that is flowing to you. So whenever we will talk about before observing data, any information coming our way, it would be encapsulated in form of prior distribution in the Bayesian context. When we talk about observation data, it is incorporated through likelihood function. Likelihood function is another keyword coming here. So those who have some exposure to machine learning or data sciences, you might have heard terms like maximum likelihood estimate or MLE for parameter estimation. This is the same likelihood function that we are talking about here, that given that certain data has been observed, uh, what is the what particular value of mu would explain that. So that's conditional probability that we are going to talk mathematically in more detail. And when we combine prior distribution with likelihood function, we get posterior distribution. It's a multiplicative form of prior and likelihood. Posterior means after, prior means before. So before you had certain information, a prior information about the system, some data came to you, you assimilated, combined that particular data with prior information, your information gets updated posteriorly, and hence the name posterior distribution comes into picture. So let us talk about what kind of information would be available as prior information or prior knowledge. That it would be typically coming from previous studies and expert opinion. As I said, you went to a site and you met somebody, and that person told you, expected flood here every monsoon is 5 feet. They did not present you with any data stream. They just gave you a number, and that's a prior information about something. And they said 5 feet plus minus 0.2 feet, there is some uncertainty involved. So the mean itself, the prior mean itself has some uncertainty associated with it, which would be encapsulated in form of variance. Similarly, variance of flood is believed to be around 0.25 square feet with moderate confidence. So again, variance also has its own uncertainty. So we can express this prior distribution assuming that these follow normal distribution, and they can take any functional form as we have learned. But for simplicity, we can assume that mean and variance themselves are following normal distribution. We can say that mean is itself a normal distribution with mean of 5 and standard deviation of 0.5, and of course variance of 0.5 square. Similarly, since variance had moderate uncertainty, we said that its variance is lesser than what mean had, and we already knew that variance is around 0.25 feet square. So these two parameters, mean and variance, now are expressed in form of distribution themselves, and hence we call these as prior distribution, right? And this prior then would be combined with likelihood, and we would be updating our priors and likelihoods into posteriors. So for example, Now, after establishing prior beliefs, we set up a station and started collecting our data. When we started collecting our data, we observed these 5 flow depths. These are exactly the same that I used to estimate mean and variance, so that we don't have to unnecessarily repeat the calculations. These samples come out to be 4.5, 5.1, 5.3, and so on. And this becomes, if I just ignore the prior information and focus on this data, I am going towards classical approach. If I account for this as well as prior information, I am going towards the Bayesian approach. And these observations themselves are the evidence that we have now collected about that particular phenomena under consideration. And then we represent this as a likelihood function. What likelihood function is? Likelihood function represents probability of observing the data given certain parameters. Remember, we are observing samples, but we are concerned about the population itself. So, given certain parameters of population that we don't know yet, what are the chances that this particular data would be observed? Right? So, we always write this as a conditional, that probability of observing given data or a data stream that we may typically represent as vector. So this case, this can be written as x vector because it's a collection of numbers. So probability of observing x vectors given certain value of mean and sigma. This is our likelihood or evidence that we are having about this. If our samples are independent and identically distributed, I can simply say that this is nothing but probability of observing x1 given mu and sigma multiplied by probability of x2 given, x1 given mean and sigma, given mean and sigma, and so on. So it takes the multiplicative form if my samples are independent and identically distributed. And this entire information is encapsulated in the likelihood term, or sometimes we also call it as evidence term. Or mathematically, evidence and likelihood have certain distinction, but in many engineering contexts, these two words are used interchangeably. But it is essentially for different values of mu and sigma, whatever maximizes probability of observing that particular x, that is the most likely value of the parameters of that particular phenomenon. So now if we have to look into the exact functional form of this likelihood of the observed data, we can simply go with mean and variance as the two parameters. And given that we know mean and variance, probability of observing a particular sample mean, given that sample mean is following a normal distribution, can be written as 1 by square root 2 pi sigma square by n. From where it comes, we'll talk about that. Exponential of minus x bar minus mu square upon 2 sigma square by n. Now, if you remember, when we were talking about normal distribution, we were saying probability of x being a random variable, and if x follows a normal distribution, it is simply given by 1 by root 2 pi sigma square into exponential minus x minus mu square divided by 2 sigma square. Now, if we draw parallel here, the functional form remains similar with certain changes in the terms. And let's try to understand that what these terms are getting changed to. Here, instead of sigma square, we are using sigma square by n. X takes the form of x bar because here x bar itself is our random variable. What we are trying to say is that we have observed a sample. From sample, we got the sample mean. But that sample mean itself would have uncertainty. For example, if you observe different batches of sample, x bar will keep on changing. And then we can draw a distribution around that which would resemble a normal distribution. And that's why x bar itself can be treated as a random variable with its own parameters of mean and sigma, which essentially represents population mean and population variance. And that is what this particular expression encapsulates. Now, the variance of this particular probability of x bar given mu and sigma square variance for x bar becomes x sigma square by n, and from where this n comes into picture, let us try to talk about it. A very, very fundamental theorem in probability and statistics, what we call as central limit theorem. So now let us talk about this rationale of having 1 by n with sigma square in our previous expression. So this originates from central limit theorem, which itself states that for very large n, if we are taking samples again and again with or without replacement, each time we will end up estimating some sample mean. And if we plot the distribution of sample mean itself, it would resemble a normal distribution. And that is where we say that the distribution of sample mean x bar approaches a normal distribution for fairly large n. And when we talk about variance of the sample mean itself, variance of sample mean would be variance of x bar, and we know that this x bar is summation of all the values of x1, x2, x3, x4 and so on divided by total number of samples that we are talking. This is how we calculate mean. Now, if you recall that variance of ax, where x is random variable, can be written as a square variance of x. So we can apply the same math here, and we say that variance of 1 by n summation of xi's can be written as 1 by n square into variance of summation of I from 1 to n xi. Now we can expand this summation and say that this is nothing but variation of x1 plus x2 plus x3 all the way till xn. This is again can be written as 1 by n square variation of variance of x1 plus variance of x2 plus variance of x3 all the way till variance of xn. If x is independent and identically distributed variable, their individual variance would be nothing but sigma square, and we are having n such terms, so it becomes n times sigma square. We already have one n sitting outside, so it becomes sigma square divided by n. So the variance of sample mean is population variance divided by n, and that is why when we were talking about probability of x bar given mu and sigma square, instead of using sigma square only, we use sigma square divided by n. When n tends to infinity, what does that mean? It means that we have high confidence in the estimate of sample mean itself, and hence variance it's sigma square by n would tend to 0, which is the measure of uncertainty. If we have smaller sample size, this particular term would get a significant weight in this entire formulation and hence becomes important. And it intuitively makes sense that given that we have larger samples that we are observing and hence having larger data points to draw inference about sample mean, the variance would shrink thanks to the central limit theorem that we have been talking about. And implication also translates that as sample size n increases, variance of sample mean x bar decreases, making estimate of mean more precise. With that, we have now all the ingredients to start combining prior with, I should not say the word evidence we can use here in a sense that, when we talk about data that we are observing, it is estimate. When we draw the distribution around that particular data, that is probability of D without any conditionality, we call it as marginal likelihood. But data D itself is evidence, because that's what we have collected. So when we talk about evidence, we are talking about data and not its probability distribution. But what we are more interested in here is that how we will combine this prior information with new evidence to update our beliefs about the parameters. And this is where Bayes' theorem, the form that you are familiar with, comes into picture. I have deliberately not stated it in a way that you may be familiar with. Probability of A given B is equal to B given A times probability of A. But because we are using it in purely data science context, I have stated it in the terms of the terminology that we will use again and again in the discussions in estimating parameters or in the context of decision making. So what Bayes theorem states that? Bayes theorem states that probability of mu given x bar is equal to probability of x bar given mu into probability of mu divided by probability of x bar. To keep things simple, this notation may get you confused very easily, so it's better to name them. We have been talking about that use of Bayes theorem is to combine prior with evidence. This is prior, some probability about mean. This is that given certain x, we are interested to update our belief about mu. This is unconditional. And this is conditional on data that we have already observed. Right? This does not worry about any data. This is some prior belief we had. This is updated. And how this updation is done? We multiply it with likelihood function. We already spoke about likelihood function. Given that particular value of mu, what are the chances we will observe particular vector x or a particular value x? And in denominator, we this have as evidence and sometimes also called as marginal likelihood. Now, we are interested in determining value of mu when we are talking about parameter estimation. And evidence, once you observe an evidence, evidence is not going to change when you are coming to the stage of estimation of parameter. So many times in data science context, we write this as probability of mu given x bar instead of taking equal to, that it is just proportional to numerator, because denominator will be same if our task is to estimate the value of parameter itself, given that now evidence has been obtained. Evidence is not changing every time, so why to carry the burden or mathematical complexity of denominator with us every time? So we simply say that this is equal to probability of x bar given mu into probability of mu. To state it simply, we can also say that posterior is directly proportional to product of likelihood and prior. Right? And that is what Bayes' theorem is. How do we reach here? Let us again look into that. This is a very quick recap of what you might have again learned in your high school or senior secondary schools, that when we talk about joint distribution of two variables, let us say x bar and mu, we can write it as probability of x bar given mu into probability of mu. We already discussed that in earlier module. These two can also change their place because here order does not matter. So we can also say that probability of x bar given mu is equal to probability of mu given x bar into probability of x bar, using same analogy that we used in equation A. Now equation A and B on left hand side, they are essentially representing joint distribution of two random variables, x bar and mu in that case. And these are two equal. So we can equate the right hand side of A and B. Once we do that, we end up with probability of x bar given mu into p mu is equal to probability of mu given x bar into probability of x bar. And once we rearrange that, we end up with this simple, beautiful form of Bayes' theorem, which there is no need to memorize it. If you know that how this very elegant, simple relationship is derived, you would never be confused which term to put in numerator and which term to put in denominator. And for us, the most interesting part would be this, that is product of prior and likelihood, and we would not worry about the evidence once it has been observed again and again in this particular case. And that's what we call as the proportionality form in Bayes' theorem. What it says, probability of mu given x bar is proportional to probability of x bar given mu into probability of mu, and this is the form that you would encounter a lot whenever discussions happen around parameter estimation. Another way to look into denominator is that it is a normalizing constant. It also ensures that probabilities of mu given x bar, they sum to 1, because that's a requirement for any distribution or any function to qualify as a distribution, that its sum from minus infinity to infinity should be 1. So this denominator that we now have dropped can also be thought of as a normalizing constant, and it does not influence the shape of the distribution. So even if we are working with this proportionality form or exact form, of course the final values may differ in magnitude, but the functional forms will not change, and we are more interested in the functional forms whenever we are talking about parameter estimation, because our objective is to maximize the likelihood that for what particular parameter we are observing that particular data with high confidence, that what we call as likelihood, and that's why this relative magnitudes would matter than the absolute magnitude, and hence proportionality constant can be dropped. Now let us affirm this particular concept with help of an example. Again, I'll bring back the flood example. So this is the same site where you went and asked people around that, hey, have you observed any floods here? Local people said that yes, we have observed some floods with mean depth of 5 feet, and we have moderate confidence on this. That's a prior information. Prior information more often than not is fuzzy. It is not crystallized. If you have a complete description of a system, then why we need probability, right? There is an uncertainty, that's why we need probability. So they would give you some estimates of mean with some unknown, some uncertainty. Then similarly, that this and they may say that, although 5 feet has some uncertainty, even that is variable. Even that estimate of mean itself has its own variance, and you end up with these two parameters that you end up from interviewing people, talking out to people, or making some judgment about the system. You get two priors, and then you set up your gauge there. You started observing that data for 5 years. You made these particular observation, and you said that, this is the sample mean I have observed, and this is the sample variance I have observed. Right? Now, question is how to combine this prior information with new evidence. This is evidence that you have generated. And this is what we will achieve through the math that we have already learned. Now, if you look into mean itself has a distribution. Why? Because localites told you that, mean itself has follows a normal distribution, and it has its own mu naught and tau naught. This is what people told you there, that this particular value takes value of 5 and tau naught takes value of 0.5. This is strictly talking about distribution of mean itself, and these are the two parameters that we specified for mean, 5 and 0.5. So tau naught is known to us, mu naught is known to us, so we know complete descriptor of prior of mu. We need not worry about sigma, because to keep things simple, we will just assume that our task is to estimate mean itself, and variance of population is known. If variance of population is not known, maths get too cumbersome. But right now we are saying that mean unknown and variance somehow is known. And we can have all possibilities, mean known, variance unknown, both of them are unknown, and so on. But to keep things simple, mean is unknown and variance is known. Again, we are having information about sample variance. We don't have information, we have information about sample mean. We are interested in sample variance. When we say that variance known, Of course, we can always calculate the sample variance, but in this case, we also have been given that population variance is known to us somehow. So both of these are known. When we talk about mean unknown, that implies that we of course know sample mean, which we can compute, but we do not know the population mean. That is not known, and identifying what is not known is the task at hand, and we have some prior information, and using that we want to determine the posterior of mean, combining prior and likelihood. Now, we already learned this likelihood function, that given sample mean x bar and known variance sigma square, how the probability distribution of x bar given mu would look like. Now, I'm sure you are familiar with this. Sigma square by n comes from central limit theorem that we already discussed. Our random variable is x bar minus mu 2 sigma square by n. Only unknown here is this. Everything else is known to us. This is known, this is known, this is known, this is known, this is also known, this is also known, this is also known. Right? So one equation, one variable looks easy, but when we will go into multiplicative form, it will become cumbersome, and that is the reason we are starting with one unknown thing at a time. Again, we will use all the simple elements that we have learned. Bayes theorem comes into picture, that too in proportional form, which says that probability of mu given x bar is probability of x bar given mu into probability of mu. If this is clear, all we have to do is substitute the expressions of probability of x bar given mu, which is likelihood, and prior. This was our prior, mu naught minus mu naught square upon 2 tau naught square. So I will just highlight these in two different colors. So this goes here, and I will color the second part as green, just substituting the expressions that we wrote earlier into this particular expression. Now, since this is two exponents multiplied by each other, I will go over the math a bit quickly because this is straightforward manipulation of these particular expressions, so I would not worry. What I am more excited is that how the end form would appear. But when we can simply say that e raised to power a into e raised to power b as e raised to power a plus b, and this is exactly what we have done here. When we simplify it, we separate the terms here such that sigma square terms come separately and tau naught square term comes separately. This is variance of mean in prior, and this is known population variance. Right? This is the same expression that is going on. We do separate all the terms, right? But this is essentially what you are looking at. This is the expression, but we want to arrange it in a way that we can draw some sense out of the mathematical form that we end up, which is easy to internalize and understand. So after rearranging all these particular terms, what we end up with is the form that looks something like that. This term can be written as, we call this as mu posterior, and we call this denominator as tau square posterior. What is important here is that if I simply collect all these terms and define that this is mean posterior, I simply say that probability of mu given x bar is proportional to an exponential function of minus mu posterior divided by 2 sigma posterior square. If you relate it to a normal distribution also says that probability of x is proportional to exponent x minus mu upon 2 sigma square. Instead of using mu and sigma, now we are using the posteriors that we have obtained after combining, multiplying and rearranging the prior and likelihood together by observing all the mathematical operations in sequence. What it means that if our prior is normal distributed with known since it's a known prior mean and associated variance, and our likelihood is also normal distributed with known variance, posterior also takes the functional form of a normal distribution. Now, this is where Bayesian theorem or Bayesian approach gets tricky. If I have unknown variance, for example, this entire process would not be as simple or as straightforward, because my prior and posterior in that case will have different distributions, which may not be easy to trace mathematically. Hence, we often start with some known functional form of prior, so that when that is multiplied with the likelihood, we end up with the same functional form of posterior as was prior, and we call such setup as conjugate priors. When posterior and priors, they have same functional form. As in this case, our prior was normally distributed. Our posterior, after rearranging, also takes the form of or the exponential form that resembles a normal distribution. So in this case, these are indeed conjugate priors. Now, if we pay attention to this particular estimate, what it is also telling us, it is telling us that mean posterior is the weighted average of sample mean and prior mean. This is our sample mean. If you look carefully, this x bar is our sample mean. This mu naught is our prior mean. And they are multiplied by two constants here, because n is known to us, sigma square is known to us. Here, both these terms are known to us. Here, in denominator, we also have n divided by sigma square and 1 divided by tau naught square. I can write this form as a times x bar plus b times y bar divided by a plus b. This is simply weighted average of x bar and y bar. This is conveying that posterior mean in this particular case is nothing but weighted average of prior mean and sample mean. If prior mean has more uncertainty, it should receive lesser weight, and that is evident here. More uncertainty means value of tau is high. If tau tends to infinity, denominator should tend to 0. That means prior mean should receive less attention or less weight. Similarly, if population variance has high uncertainty, sample mean should receive less weight. So in that case, it becomes a very simpler way to internalize it, that it is nothing but weighted average of prior and sample mean, and this weighing is happening based on how much uncertainty is contained in that particular information. So very complicated concept, essentially boils down to that if you indeed have a normal prior and likelihood function is also normal distribution, the posterior of mean would be also a normal distribution with the mean coming out to be the weighted function of the prior and the likelihood or the sample mean that you have observed. Now, if we have to put this in action, we will simply use this particular formula as an end product and try to update our prior information with what we have observed. So in this case, prior flood depth was normally distributed with 5, 0.5 square. Since variance is known to us in this case, we are not going with estimation of population variance. So I have dropped that second equation about prior information for variance. So we'll just focus on prior for mean flood depth mean. You went there, somebody told you, you took that to face value. Okay, I'll assume that this is true. This is prior. You will update your final estimate of mean by collecting an evidence. So you collected an evidence, 4.5, 5.1, 5.3 and so on. You calculated sample mean and sample variance. To keep things simple, I am assuming that sample variance is also equal to population variance in this case, if I don't have any other information, which is totally fine. If some exact value of population variance is known to you, you can also use that, because as I discussed earlier, population variance and sample variance need not be equal to each other. But here I am assuming that these two take the same value. Now, what we are asked to calculate posterior mean. We already looked into the expression n x bar upon sigma square plus mu naught tau naught square divided by n sigma square plus 1 by tau naught square. For us, this was A and this was B. So I'm just highlighting all the terms of A and B. So this was B for us and all blue colors are A for us. So A x bar plus B y bar, and they are just weighted divided by A plus B. So let's substitute the value, and this in this case is 5 because we only made 5 observations. X bar is sample mean, which we observed as 4.94. We assume that population variance is same as sample variance in absence of any other information. We calculated this value as 0.138 in our earlier example. So 5 goes here, 0.138 goes here. I hope that we know what we have substituted here. Now we move to the second term that is equivalent to the prior terms. For prior, we already knew the mean, mu naught, which was given to as 5. So we substitute 5 here. Tau naught square, that is variance of prior, was given to us 0.25. We substitute it here. We take the average and it comes out to be 4.96. If you just looked into samples, our sample mean was 4.94. Right? If we just calculate this mean, this was 4.94. Our prior mean was 5. It is expected that posterior would be somewhere between that because it's a weighted average of these two quantities, and this is exactly what we observe. But now we have improved the estimate from 5 to 4.96. We have also included the prior information and corrected the sample mean to 4.96 from 4.94. In this simple example, we only had 5 observations, and if you look closely, these 5 observations were very close to each other also, and that's why you don't see much fluctuations in the answer. But now, if you talk about a real world phenomena where you have 30 observations and you have a noticeable variance and prior is far away from the sample mean, you don't want to neglect the prior, you also want to account for your observational data. This is where you would see the dramatic changes happening in your posterior means when you combine this likelihood and priors, but essentially the math remains the same. So I have broken this into various components, but this is essentially what we have plugged and played here. You can think of it as tau posterior coming into picture and so on, but that essentially covers that how Bayesian comes into action, where it's the posterior mean, which is weighted average of prior mean and the sample mean. We may keep on talking about Bayesian distribution, all the complex mathematics, but this is the insight that is a big takeaway for us, that what Bayesian approaches essentially do for us when we have to combine prior with the evidence and associated likelihood. And here we also observed that the posterior variance is smaller than both prior variance and sample variance, which also reflects the increased confidence in the estimate. What exercise we did for mean, we can also look into tau posterior, and in this case we get tau posterior as 0.025, which happens to be lower than the variance of sample and priors looked separately.
And what does that mean? That now we have more confidence, because variance relates to the confidence and uncertainty, and this is essentially what it helps us to do. In following discussion, we'll talk about Bayesian approach for discrete cases, because because the data streams that we get, they may have observations spaced discretely. How to use the same Bayesian framework or thinking in that particular paradigm, that we will discuss next. Thank you. All right, let us move to our next case on Bayesian approach for discrete cases. First of all, why it is useful. This form or a discrete form of Bayesian approach becomes quite useful when we have to estimate parameters of a particular distribution, because whenever we will be observing data sets, they would be in most of the cases, be it flood depths, be it rainfall level, it will be observed discretely. That is, first measurement will come, and second and third, and so on. So in that case, the vectors of observation x bar can be written as collection of x1, x2, x3, and xn, where these are individual observations at discrete time steps. Please note that when I'm talking about discretion here, it's not that x1 can only take discrete values. X1 can be continuous, but the observations are being made at discrete time steps, and hence this vector would have form n cross 1, and all these observations are occupying a discrete position in this particular vector. And now we have to apply this Bayes theorem to this discrete case. Let's see how we would do. A quick recap. We already learned that probability of A given B can be written as probability of B given A into probability of A divided by probability of B. This was our likelihood. This second term was our prior, and this was marginal likelihood, where B was our evidence. And now if we have to apply it to discrete case, what we can simply do is that what we were doing when we were talking about one variable, the same reasoning can be extended to n variables, and we say that probability of getting a particular theta given x1 all the way till xn can be written in the same form, where we replace x as x1 to x2, x3 all the way till xn given theta into probability of theta divided by probability of x1, x2 till xn. Now, if our observations are independent and identically distributed, we learned that probability of A and B can be simply written as probability of A times probability of B. Same reasoning can be extended if you have A, B, C, D, E all the ways to probability of A into probability of B into probability of C all the way for whatever is your vector length. And what we do for summation, we have a similar notation for multiplication, where we say that I equal to 1 to n multiplied, where this is probability of xi given theta. And now we keep on, instead of summing, we keep on multiplying it as probability of x1 given theta into probability of x2 given theta into probability of x3 given theta, and so on. And this applies when our observations are indeed independent. When we put this all together, our Bayes theorem with IIDs in discrete case looks like probability of theta given vector x as multiplication of all these discrete observations of xi's given theta into p theta. And again, denominator would not matter to us, so I have kept it unaltered. But I can simply say that this particular term is nothing but it is probability of x vector. Now, if this is clear, we are good to go into diving a bit more into likelihood, because that's what would form the foundation of our parameter estimation. In case of observations which are independent and identically distributed and observed at discrete time steps, our likelihood function takes the form of probability of x1 to xn given theta as multiplication of xi given theta, where I varies from 1 to n, and all these terms are multiplied. And this is the form of likelihood that would be largely used in parameter estimation. Now, we have been talking about likelihood. Our task is to estimate parameter, and these two words become important whenever we have to talk about parameter estimation. That is, we want to maximize that particular value of likelihood for whatever value of theta, such that my entire likelihood gets maximized. Let us put it in simpler terms. For example, I have made some observation, and I will just keep it simple that there are three values that I have observed: x1, x2, x3. Right now, I don't know that what is the value of parameter. Let us say mean is the parameter of interest, and I am not simply going to use x1 plus x2 plus x3 divided by 3 as mean. I want to estimate it mathematically, that why mean in this case is x1 is indeed x1 plus x2 plus x3 divided by 3, because if in other cases I would not even know that whether this is mean. So if I remove this, it may be simply given to me that, one of the parameters here is theta 1, estimate theta 1. I don't know the name of this parameter. I only know that mathematically it's some theta. Now, I can do a grid search. I can say that this particular theta can assume value of 0.1, or this can assume value of 0.2, or this can assume 0.3. There are infinite possibilities, but to keep things simple, it can only take 3 values. And I know some functional form between x1 and theta. That is, I know that how this likelihood function is going to look like. That is, probability of x bar given theta is known to me. To keep things simple again, I can simply say that a functional form, it would not be as simple here, but again, I'm not worried about the integrity of probability function here. Let us say that function is some theta times x minus theta square times x. This is functional form of x given theta. Something is known to us. Now, I have to find out what value of theta is the best value. And I am assuming that this is some sort of probability function, x given theta. Now, intuitively, I should go with that value of theta that should maximize the value of function, because in this case, it's probability. That if I take this particular value of theta, chances of observing this vector gets maximized. And it stems from the fact that chances of observing the one particular value gets maximized, and second value gets maximized, and third value gets maximized, and so on. If my samples are IIDs, I have emphasized this earlier also, that if I am using word and with such a stress, it is nothing but multiplicative factor coming into picture. So whatever maximize the multiplication of a given b and x given theta and x2 given theta and x3 given theta, that is the most likely value of my theta, because that is maximizing the probability of observing that particular vector that I am observing, and that is why it is called as maximum likelihood estimate. Now, in mathematics, whenever we have to find maxima or minima of any function, we typically go for the differential. That is, we would differentiate it with respect to that particular variable, equate it to 0, check the sign of higher order derivatives, and conclude whether that particular point is maxima or minima. And that's why this becomes a problem of unconstrained optimization. And here our variable of interest is the parameter itself, that just give me the data, give me some functional form that relates data to the parameter. I can really find what is the best parameter of best value of that parameter based on the observations that I have made. So mathematically, this is typically written as that maximum likelihood estimate of theta is that value of theta that maximizes, argmax means that particular value of theta that maximizes the value of this particular argument, which is p of xi given theta. One way, as I said, is grid search. Keep on putting in values of theta, make a table, find that particular value of theta that maximized your probability. Another way is to find a closed form solution by taking the differential, equating it to 0, which we will do in this particular case here to find these particular value of theta that maximizes this entire argument. Even if you are lost in mathematics, it will get clearer as we will do a couple of examples. But please pay attention to this, because parameter estimation is backbone of any data science approach, which again informs a lot of decision making processes that we are going to talk subsequently in this particular course. So now if we talk about likelihood, we learned that likelihood was nothing but it was multiplication of probability of xi given theta. If we take log on both sides, multiplication becomes summation, because log of a times b is nothing but it's log of a plus log of b. Dealing with multiplication every time is a bit tedious, hence we take the log and convert our multiplication to summation domain. So now it becomes log of likelihood theta as log of p of xi given theta, and instead of multiplication we are back to our familiar summation form, which is summation from I to 1 to n. And our maximum likelihood estimate now takes the form that argmax, whatever value of theta maximizes this argument, that is still our key question. And instead of multiplication, we are again summating this entire argument from I from 1 to n of log of p of xi given theta. Now, let us try to look into a concrete example of this abstract probability of x given theta, that given a set of observations x1, x2, x3, xn, you can think of it as flood levels observed in a particular river, and we have to estimate mean and variance using maximum likelihood estimate. We are not allowed to use our cheat code that, I know mean is equal to x1 plus x2 plus x3 summation n, and variance is equal to xi minus mu square. And that is not the point. Here is that if I replace this with theta 1 and this as theta 2 and say that they are coming from some distribution that takes of a particular functional form, how it would look like. In this case, we are assuming that they are normally distributed. So I can always write the form of likelihood function of mean and sigma square as 1 by 2 sigma square exponential minus xi minus mu square divided by 2 sigma square. Again, I am using the multiplication here because I have not taken the log just yet. The moment I take the log, this expression splits into two parts. First one takes care of everything here, and second is exponential here. So this stays as log, and log of exponent is the number itself, that is log of e to the power x is x itself. So this just remains whatever was the power of e. In this case, we end up with log as n by 2 log of 2 pi sigma square minus 1 by 2 sigma square summation 1 to n xi minus mu square. Now this is the function that I am interested to maximize. So what I will do, I will first differentiate it with respect to mean, and first term, for example, has nothing about mean. So it would be 0. It's a partial differentiation with respect to mean. So only second term will remain intact, and I simplify this particular derivation, and upon simplification, I end up with something like minus 2 xi minus mu summation I equal to 1 to n. Again, our focus is that maths, all these steps can be done, but how to do that, what is the reasoning, that is more important here. So essentially what I end up with this particular expression, I end up with minus 2 x1 minus mu plus x2 minus mu plus x3 minus mu all the way till xn minus mu. How many mu terms are here now? N terms. X1 plus x2 plus x3 are there. And to maximize it, I have to equate it to 0. So essentially, I am looking at summation of I from 1 to n xi. Mu comes outside as n mu. It is equal to 0. It comes out to be n mu is equal to summation I from 1 to n xi. My estimate of mean comes out to be xi summation I from 1 to n divided by n. And this is the expression that we have been using always, that mean is this. But here is a much crisper reasoning that y, first parameter of normal distribution, if we replace it with theta 1, is indeed the mean itself. Same reasoning can now be applied to estimation of sigma. Right now we substitute it back. I have already done this particular math, but this is the expression of interest that you all are familiar with. Even if I replace it with theta 1, we can say that theta 1 is mean itself. Right? Because by definition, this is the mean. This is the average of all the numbers that we are aware of. Similar argument we can have about second parameter, which is sigma square. We again write the same thing, log of L mu sigma square. It's the same expression that we wrote for mean. Now, instead of taking differentiation with respect to mean, we will take partial differentiation with respect to sigma, right? We can sometimes treat this sigma square as the variable of interest and take differentiation with respect to sigma square. Now, first term is important because it will not get deactivated, because there is a term of sigma square sitting here. There is a term of sigma square sitting there. So what we will do is that we will take the differentiation, and this is the expression that we end up with. Minus n by 2, 1 by sigma square plus 1 by 2 sigma raised to power 4. All other terms which are just function of mu remains as it is, as if they are constants in our differentiation multiplied by that particular variable against which we are differentiating. We equate it to 0 and we get our estimates as 1 by n xi minus mu square I equal to 1 to n. This is not exactly same as the form that we have used, but very close to the form. If you remember, I emphasize that whenever we are dealing with sample, the estimate of variance is 1 by n minus 1 I equal to 1 by n xi minus mean square. But if you see that if n is very, very large value, these two variances or these two parameters converge with each other. That means sample mean and sample mean estimated from this particular expression becomes same as population mean. But if I have really small sample size, 1 by 5 and 1 by 4, they may add certain differences or bias in our estimates. But mathematically, this is the parameter that we estimate here, right? With 1 by n, it is still an estimate. It is mathematically derived, but it is a biased estimate. Biased estimates either overestimate or underestimate the population mean based population parameter. If we go by this particular definition, and we will show why it is called as the biased estimate and so on, and why this 1 by n is corrected to 1 by n minus 1. But right now, things to focus for us. We started with Bayesian. We focused on prior and likelihood. Then we focused on likelihood. We did some mathematical operations, and we actually estimated two parameters of interest of any distribution. And what it empowers us with? It empowers us with the fact that give us any data vector, give us any functional form, we can really now estimate the parameters if we really don't know what is their exact mathematical form a priori by using a very similar steps as we have done in this particular case. As I said, that what we get maximum likelihood estimate for variance was 1 by n I from 1 to n xi minus x bar square. For very large n, both of these particular equations will give you almost similar or comparable magnitudes of variances. However, whenever we are talking about unbiased estimators, we instead of 1 by n, we use 1 by n minus 1 instead of 1 by n. And the reasoning lies in the fact that we can really show that why this would not converge to sigma square. What we have to do is that if we take expected values on both sides, we can simply write it as expectation of 1 by n and summation of xi minus x bar square. And when we take 1 by n outside, we are essentially drawing the expectation of this particular term that is sitting inside. When we expand this, we can subtract mean from both sides, and we can write it as xi minus mu, x bar minus mu, and square on both sides. If you look into this particular expression closely, we have not done anything special. We have just subtracted mu from both the brackets and then we expanded it. If you recall, we were saying that expectation of xi minus mu square by definition is the variance itself. Because when we defined variances, we defined it in terms of expectation. That is, first moment gives us mean. Second moment gives us variance, but we subtract mean from each sample and then calculate the expectation of square. And when we spoke about central limit theorem, we learnt about that expectation of x bar minus mu square is not the variance itself, but it is sigma square divided by n, or n dependency comes into picture. Right? When we plug in these two expressions here, we essentially look into this particular form that expected value of sigma square, maximum likelihood of variance, is n minus 1 into n upon sigma square. If you look here closely, if this would have been n minus 1, they would have been equal. But that is not the case from the mathematical steps that we have followed. And we end up concluding that it is biased by the magnitude, by a magnitude of 1 unit. And that's what we need to take care of, that instead of normalizing it by n, we normalize it by n minus 1 to take care of this particular variance. Although this is a very small concept, but it is very fundamental, because sometimes students get confused that, we have always learned it is 1 by n xi minus x square, then why this is being normalized by n minus 1? Because even if we have obtained an estimate, we want to ensure that that particular estimate is, that the expectation drawn around that particular estimate actually gives us the true population parameters than the biased ones, and that's where that correction needs to be done as and when needed. Whatever operation we did here, we can do the similar expectation calculation to really establish whether a particular parameter estimate is indeed biased or unbiased, even if the distribution or functional form of these particular variances change. And hence we can conclude that if we use 1 by n minus 1, the expectation indeed comes out to be sigma square, and hence it is an unbiased estimate when drawn over the population. And typically in data sciences, we define bias as that what is the true value which we represent by theta, and its difference from the expected value, what we call as theta hat. And if this particular difference is significant, we say that, or significant in a sense that if it is not equal to 0, we say that that estimator is biased. If it is equal to 0 or close to 0 within our tolerance limits, we say that estimator in this case is unbiased. Now, I hope that we have a stronger rationale that why it was not normalized with 1 by n, but we always use 1 by n minus 1 whenever we talk about sample variances and try to draw inferences about the population variance using the data sets that we observe. And this is where that n factor comes into picture, that the difference between these estimates is minus sigma square by n. So we take care of that particular bias by normalizing it by n minus 1. Now, we will conclude this particular lecture by looking into one very interesting example on application of Bayes' theorem on a real world flood example where really limited data is available to us and we want to end up with certain observations. Here, I will just brief the question and we will look into the solution in subsequent video. But here the problem is very simple. Solution may or may not be. But first of all, let's focus on the problem. Problem says that we want to model the flood depths in a given area. We have information, we have some experience that typically when we have to model flood depths, they follow exponential distribution. This distribution can be something else, but it can take generalized extreme value 1, 2, 3. But here we are assuming that it is an exponential distribution. We don't know lambda. We want to draw the probability distribution H because perhaps we want to design a dam or a flood control works there. So we need to have good estimates of H there. Ideally, what we would want to have is that we will want to have a really long time series, 50 years, 100 years time series at that particular place, a nice model, and then estimate what would be value of H. But life is not as fair as we want it to be. So we will only go with some prior experiences of the people living there because that data is really not available to us. So what we did is we went to that particular site. No official records were existing in the office, but we went to local inhabitants and started talking to them that what has happened at that particular place. And they told us that, earlier we only remember that only 2 floods had elevation of at least 5 feet. We have no other information. This is the only information we have. The question is, let us determine value of lambda and its mean value, because once lambda is known, we can really determine probabilities of any flood happening, because that is the only parameter that we are interested in. Now, with this limited information, our classical approaches fail. You cannot move an inch with classical approach because we don't have data. So now let us solve that particular example that we started earlier. So if we talk about an exponential distribution would take some form like this. It is only defined in its positive domain. That is, if this is H and this is probability of H, it will take some functional form like this, right? But we need to know parameter lambda to really determine at what rate it is decaying. And that is why it's a single parameter distribution. And if we know lambda, we know everything about this particular distribution, because boundary conditions are known that as H tends to infinity, Px tends to 0. If H is equal to 0, f of H tends to value of lambda, but we don't know lambda yet. So how we estimated lambda before? We collected the data and we knew the relation between lambda and mean. If you remember, in frequentist approach, or classical approach, it was lambda is equal to 1 by mu. But here we don't know the mu. So what we do here is that we go to the site, interviewed people, and they told that only 2 floods had elevation of at least 5 feet. That is where in statistics and probability, paying attention to these words become important. At least 2 floods. So here one keyword for us is at least. Only 2 floods had elevation of this. So we have to write this mathematically. And question is to determine value of lambda. And subsequently, we can answer questions like, what is the probability that next flood at that particular site will exceed 5 feet? So with this particular case, we can answer all these questions once we determine value of lambda. So let us put that particular information in context first. What is prior information available to us? Prior information is that 2 floods have elevations of at least 5 feet. Some exponential distribution is available and no other prior information. So we call this as a least informative prior. No distribution form is known. No domain of lambda is known, right? So this is also called as a diffused prior or uninformative prior or least informative prior, right? So we say that it is it can take any values. It is really not adding a value, and it's neither normal distributed, it's neither exponentially distributed. I'm talking specifically about the prior of lambda itself. What else is known is that two events have happened. Nobody told us whether they happened in the same year, at the same time. So it's a good assumption that they might have happened independently. As and when more data is available, then we will worry about next level of complexity, whether these two events were indeed independent or not. But right now, our best bet is to go with this assumption of independence. We learned that two independent floods exceeding 5 feet. This is the useful mathematical information I've extracted from the question given. So we can say that probability of two floods greater than 5 given lambda. So if you look into this, we are talking about probability of H greater than H. If you recall, when we were talking about CDFs and PDFs, we can say that this is 1 minus probability of H less than H. This is 1 minus infinity to H probability of H. I am simply writing it as f of H now, because this is what my cumulative distribution function takes the form of. Or here I can work with this, because once I put in the limits, then it becomes the CDF. But right now it is the probability distribution function between P of H. This exponential distribution function is strictly defined when H is greater than equal to 0. So the limits can now be changed to 0 to H P of H, which is nothing but 1 minus 0 to H lambda e to the power minus lambda H. Upon simplification, we simply get this particular expression as e raised to power minus lambda H. I will leave this simplification for you as a homework, but just substitute the limits at H equal to 0. First term would become 1, and other term will remain, which is e raised to power minus H lambda. In this case, H is 5. And since two events have taken place, it is probability of X and probability of X, square of both these terms, because these are independent. It essentially gives us e to the power minus 10 lambda. Had there been 3 events, it would have been simply 15 lambda. Had there been n number of events, it would be simply 5n lambda. Now, first question is to determine the posterior distribution of lambda and calculate mean value of lambda. We don't have much information about prior, because we have non-informative prior about lambda. See, we have information about the flood, but we don't have specific information about lambda or its functional form. So prior information about lambda is not available. Hence, we are saying a non-informative prior for lambda. And we say that it is just proportional to 1 for lambda greater than equal to 0. Proportional to 1 comes from the fact that whenever we talk about uniform distribution, which is a classic example of uninformative prior, we say that for a variable following a uniform distribution, its functional form is 1 upon b minus a, where b and a are the limits, and hence it just is proportional to 1. So uninformative prior and uniform prior is the best way to represent this uninformative prior. Now, when we talk about probability of lambda given delta, it is proportional to probability of data given lambda into probability of delta. See, we are dealing with proportionality. Hence, we need not worry about 1 upon b minus a in this particular case. That's why we simply say it is 1. E to the power minus 10 lambda we already derived earlier. And this simply becomes probability of lambda given 2 floods are greater magnitude than 5 is prior of lambda multiplied by data given lambda, which is nothing but the proportional form of Bayesian framework that we have already discussed. It gives us 10 e to the power minus 10 lambda. Now, if you focus on this particular form, this takes the form of another exponential distribution, which is of form k into e to the power minus k lambda. This is probability distribution of lambda itself. Because we were going behind lambda, we are interested in posterior of lambda and not the random variable of flood depth itself. Here lambda itself becomes a random variable under investigation, about which we want to draw the statistical inferences. Now lambda itself is distributed exponentially. We started with flat prior. Our likelihood took the form of exponential. Our posterior also took the form of exponential. And once we have determined this as an exponential distribution, the expected value of lambda would be simply 1 by 10. Because if you remember, whenever we were talking about fx, it was lambda e to the power minus lambda x. Just by looking at lambda, we can say that expected value of x is nothing but 1 by lambda. In this case, we are interested in statistical distribution of lambda itself. So we have already established that, f of lambda is equal to k e to the power minus k lambda. So this lambda now equivalent to k in this particular case, and x, which was random variable earlier, here random variable is lambda itself. So the estimate of lambda, e of lambda, would be nothing but 1 by k. We already established value of k as 10, so expected value of lambda comes out to be 0.1. So the posterior distribution gives a clear estimate for lambda, and we know that for exponential distribution, mean and variance is also related. So we have determined full parameters for posterior in this particular case. Now, if I would have changed the form, the functional form of my likelihood, the entire math will change, but the essence will remain the same. That rather than always getting fuzzy about probability distribution function of random variable x itself, you can also draw the probability distribution function of parameter itself when parameter itself has an uncertainty inbuilt. If there is no uncertainty in parameter, there is no point in talking about probability. We didn't know the parameter. Parameter is supposed to have an uncertainty based on the information we had. And that is what we quantified using this Bayesian likelihood. Now, once we have determined it, we can answer the question that we were answering in the classical approach. That would, what is the probability that next flood will have a height greater than 5 feet? Now, we are drawing the estimates around probability of lambda. Given 2 floods greater than 5, we already determined 10 into the e to the power minus 10 lambda and so on. Now, question is probability of h greater than 5 given lambda. Right? That next flood is greater than that particular value. Now, we only knew one estimate of lambda, but now we know full distribution or functional form of lambda. Now, lambda can take any value, but we know its functional distribution now, that it is exponentially distributed itself. So it has to be incorporated in our estimates of whatever calculations we are doing. So here it is nothing but it's a probability of h greater than 5. That is our key question that we have asked in a similar fashion what we would ask in a classical approach. It is probability of x greater than 5 would simply be probability of x greater than 5 given a particular value of lambda multiplied by probability of observing that particular lambda. Because we have an estimate of lambda, we have a distribution of lambda, but we don't have a precise measure of lambda in this particular case. So that has to be accounted over entire domain of lambda. And lambda can be 0 to infinity because it's 1 by mu, and it cannot take a negative value the way parameter of exponential distribution is defined. So we now say that probability of h given greater than 5 given lambda, probability of lambda given 2 floods greater than 5 over entire domain of lambda. We already knew this particular expression. We now also incorporate probability distribution function of lambda. and we integrate it over entire domain. And of course, upon integration, I'm not going into the details, but for completeness, these slides would have all that particular information. But when we plug in these particular values, we get that probability of h greater than 5 as 0.667. So how we started, we had some prior. From prior, we constructed the distribution of lambda itself, and then we incorporated that distribution of lambda in estimation of h greater than 5. This particular formulation is implicitly also used in the classical domain. How? In that case, for a particular value of lambda, we have probability of lambda equal to 1 at that precise estimate, and everywhere else it is equal to 0. So there is no need to do an explicit integration there. But when lambda itself is distributed by some function, the probability would be highest at mean, and this particular formulation will capture that. It will decay to 0 as we go towards infinity. This particular function will capture that because its mathematical form 10 to the power e to the power minus 10 lambda has that particular information, that when lambda tends to infinity, probability of observing that lambda tends to 0, and hence all the values or possible values of lambda has now been accounted for in estimation of this particular probability. And this is where Bayesian approach comes into picture. This is nothing but this is the total probability coming into action when your h is conditional on lambda, and conditional variable itself has uncertainty. That uncertainty is represented as probability distribution, and you integrate that over entire domain of that particular probability distribution. And hence we end up with this particular mathematics, where we end up with some 66.7% probability by following all steps logically and using the math established. Next part is that now 3 new floods have occurred at a given site. After this entire information was available, field survey was done. Now you have taken control of that particular site, but now 3 more floods happened in subsequent year, and their depths were 3 feet, 4 feet, and 5 feet. Now our next objective is to update the distribution of lambda with this new information. So far, we have reached to a point where we estimated that, based on what local inhabitants told us, lambda is exponentially distributed with these particular parameters. Now, when new information is available, what may happen is that distribution of lambda may change, or parameter of distribution of lambda itself may change. How to incorporate that information? That is what we are going to discuss in the next class. Now, here are 2 things that I would like you to pay attention to. All these concepts, they may appear a bit difficult when you just look it from mathematical perspective, but this is how real world problems need to be solved, because real world problems are not simple. When an event is happening, a manifestation of an event is happening, it is interacting with our complex environment around us. So there is only up to a level we can simplify that particular setup and try to draw inferences. But even with limited information, these tools of classical as well as Bayesian approach really power us to get much better estimates of hazards. Because whenever we have to talk about risk assessment or resilience quantification, hazard quantification remains its central core or central piece. Without that, we cannot move to advanced concepts of decision making. Whenever we will talk about the concept of risk management, we will be using values of risk that would be calculated a priori or actively using the information and frameworks that we have covered till now, and there would be very less mathematical surprises when we will go to our core discussions on decision making and decision tree and risk management. Thank you. So now let us look into example of Bayes theorem's application to our flood example.
This particular example would be mathematically involving, so we'll ensure that we write all the steps slowly and carefully to ensure that we fully understand how to deal with problems which have limited data available a priori. So the question here, I'm just restating it so that we get time to internalize what is given, what is being asked. So here it is given that the maximum flood water level H during flood can be expressed using an exponential distribution where f of h is lambda into e to the power minus lambda h, where lambda is the parameter and h can only be greater than equal to 0. So what does that mean? That whenever we are going to integrate over h, our limits are always going to start from 0, and upper limit could be level of interest, or if we are interested to derive the expectation, it could go from 0 to infinity. Then second point says that no official records exist on the site, but local inhabitants recall that during earlier floods, only 2 floods. So we will again highlight this important piece of information. Only 2 floods have had elevation of at least 5 feet, and it can be assumed that floods are statistically independent. Of course, locals will not tell us that particular information, but that is the best assumption we can make as statisticians, engineers, scientists, in absence of any other information, so that we can take first step toward modeling these particular events. And no other information is available about lambda. Only thing we know about lambda is that it being a parameter of an exponential distribution, lambda can only take values greater than or equal to 0. Other than that, we have no other information. And we are asked to determine the distribution of lambda and its mean value, because once we have distribution of lambda or its mean value, we can determine various probabilities associated with different heights of flood in that particular case. So what we will do, first of all, we will write down all the information that is available to us. We will start with prior information. What is given to us in prior information? Let us write it down. Nothing is known about lambda. This is also an information even if we know nothing about lambda, because that will help us assume the prior. Since here we have no information about lambda, this prior would be uninformative prior or flat prior or diffused prior, which is not conveying any specific information. So lambda can uniformly take any value over its domain. So what we would say is that whenever we have to talk about prior distribution of lambda, all values are possible. In denominator, we will have some range b minus a. So we can only focus on the numerator, that is, it is proportional to 1, that is, all values are equally likely in the domain of lambda. Another information that is given to us is that only 2 floods of magnitude 5 feet, greater than 5 feet, took place. And third thing that is given to us, that H follows exponential distribution, and its functional form is given as f of h equal to lambda e to the power minus lambda h, and h is greater than equal to 0. Another very important information that is given to us is about independence of events. What does this independence of event mean? That if we have to write probability of 2 floods greater than 5 feet, we can simply square probability of 1 flood greater than 5 feet, because these 2 events are independent, and hence probability of A and B simply becomes probability of A times probability of B. So when we are talking about probability of 2 floods greater than 5, that is as good as 1 minus probability of H
less than 5 and its square root. This square comes because when we talk about one flood, we can simply consider 1 minus probability of h less than 5 and events being independent. That gives us liberty to use this particular square term because there is no joint distribution involved given the independence of these particular events. Why we write probability of h less than 5? Because that essentially represents the cumulative distribution function, and doing math around cumulative distribution function would be much easier, as we will illustrate just now. So we can write this as 1 minus integration 0 to 5 lambda e raised to power minus lambda h dh, and this will have square of both. We can write this as 1 minus lambda upon lambda. Since it is e raised to power minus lambda h, one lambda would come in the denominator and this would convert this to positive sign, e raised to power minus lambda h, and our limits remain 0 to 5. And when we substitute that, we get 1 plus e raised to power minus 5 lambda minus 1 and square of its whole, because e raised to power minus 0 becomes 1, e raised to power minus 5 lambda stays as it is, and these two ones cancel out each other, and hence we get e raised to power minus 10 lambda as probability of two floods greater than 5 feet. Now this gives us good starting point to move on to the determination of posterior of lambda in absence of an informed prior. As I mentioned earlier, we have uninformative prior for lambda, but using whatever information we have, we need to know the best possible probability distribution function of lambda so that we can do the mathematics around that and determine the values associated with different levels of flood heights, which is our question of interest. So now let us focus on lambda. Yeah. So now we will focus our discussions on lambda. So we are interested in probability of lambda given some data to us. If you recall, we learned that we can only focus on numerator of Bayes theorem, and we can write this as probability of data given lambda multiplied by probability of lambda. We call this particular term as prior. This was posterior and this was likelihood. And we already did lot of derivations using this particular likelihood, but in this context I am getting rid of these terminologies as we have already discussed these in details, and we can focus on our question of interest, which is determining the posterior of lambda given some information. Now in this particular case, probability of lambda is uninformed prior. Hence we can simply say that this would be some proportional to 1. What data is given to us? We are only given data about two floods greater than 5 feet. So we can rewrite this particular equation as probability of lambda given two floods greater than 5 feet is equal to, I will remove this sign of proportionality using a constant k that I don't know yet, but I will determine probability of data given lambda. If you recall, in previous slides, we derived probability of data in terms of lambda, which was given as e to the power minus 10 lambda. So we have already derived this probability of data given lambda as e raised to power minus 10 lambda. And as I mentioned, probability of lambda is proportional to 1, and our constant of proportionality should take care of all the constants that we might have not explicitly written here as we normalize. Now, if we focus on this probability of lambda greater than 2 floods greater than 5 feet, it is equal to some k and lambda. Now, this is a probability distribution function, and for this to qualify as probability distribution function, its integration in its domain should be equal to 1. Now, lambda always takes the positive value, that is, it can only be greater than equal to 0, it being a parameter of an exponential distribution. So, this particular integration from 0 to infinity, not 0 to 1 but greater than 0. So, lambda has the domain from 0 to infinity. So, that's where we will integrate and equate it to 1. Probability of lambda given data should be equal to 1. That also implies that 0 to infinity k into e to the power minus 10 lambda into 1 should be equal to 1. And when we integrate it, substitute all the limits, we get value of k as 1 divided by 0 to infinity e to the power minus 10 lambda into d lambda. Of course, we have to do an integration with respect to lambda in this case because that's our variable in the posterior for which we are finding this constant of normalization constant. And when we put the values, e raised to power minus infinity tends to 0, e raised to power minus 10 lambda would give us 10 in numerator, and with negative sign we get minus 1, and hence constant of integration comes out to be 10 in that particular case. Now that we have introduced k as 10, we can write probability of lambda given data as 10 into e to the power minus 10 lambda. And this is also an exponential distribution with parameter 10. Please understand that this is an exponential distribution of lambda. H also had an exponential distribution with different parameter, which was lambda. But here lambda itself is uncertain. We do not know the precise value of lambda, and we did all this exercise to determine that my parameter is also following that particular distribution and what is the mathematical form of that distribution. And that is why we have done all this particular exercise to determine the probability of lambda given data. Now, if we have to make an observation of posterior distribution, we agreed that lambda also follows exponential distribution. Parameter of that particular distribution is 10. And if we know that parameter of exponential distribution has a value of 10, which in this case is equal to k, we can always derive what is the expected value of lambda. It is nothing but 1 upon k or 0.10 in that case. Because now we know the distribution, and hence relationship between the parameter and first moment, second moment, third moment and so on can now easily be established using the functional form of the PDF itself. Now, this is great. We have determined something about lambda. Next question arises that with this particular information, what is the probability that next flood will have a height greater than 5 feet? We again would use same posterior distribution for lambda that we have derived, k e raised to power minus k lambda, and in this case value of k is equal to 10 as we already established. We started with information that we got from local inhabitants. We applied Bayes theorem on that particular information. updated information about lambda, and now we are using that information to make a decision or determine further estimates about the floods. And that's where Bayes theorems becomes quite powerful when you have limited data. And this particular example is a very good demonstration that how we can start from very limited data to get insights that are actionable and usable in our decision making framework. Now let us go to this particular part, that how we are going to solve this. Here we are asked that what is probability that h is greater than 5. That is the question. We can simply write this as probability of h greater than 5 given lambda and probability of observing certain value of lambda. Because we don't know the precise value of lambda, lambda itself is uncertain, it has its own distribution. So whatever probability of height we will determine, it is conditional on value of lambda. When we were talking about classical approach, this probability of lambda was reducing to 1, and hence we need not talk about the conditional dependence of h on lambda because value of parameter was precisely known. But in this case, we do not precisely know the value of lambda, and it can take value over certain range. Hence, we have to look into probability of lambda taking certain value in its domain, which can go from 0 to infinity, its probability, and if it takes that particular value, we then have to conditionally derive probability of h greater than 5 given that particular value of lambda. Now we can focus on the left hand side and again write probability of h greater than 5 given lambda as 1 minus probability of h less than 5 given lambda. Again same thing, we will go from the probabilities of exceedance to CDF by subtracting it from 1. This again can be written as 1 minus integration of e to the power minus lambda h lambda with limits from 0 to 5, because we are interested in probability of h less than 5. H cannot take values less than 0, hence limits become 0 to 5 and integration with respect to h given lambda. What is the value of probability of h less than 5? When we solve this integration as we did earlier, we again end up with the form 1 plus e to the power minus 5h minus 1, because again lambda e raised to power minus 0 would give us 1, negative is sitting outside and hence they would cancel out each other and we get this particular value as e to the power minus 5 lambda. Now we will plug this particular value in our previous form. Probability of h greater than 5 can now be written as e minus 5 lambda, and we have updated probability distribution of lambda from our posterior, and hence we can write this as, this would be multiplied by 10 e raised to power minus 10 lambda and integration with respect to d lambda, and this would take values from 0 to infinity. And when we solve this, we are essentially looking for 10 into e to the power minus 15 lambda d lambda, and here limits are 0 to infinity, and when we integrate this, we are essentially looking at 10 comes outside minus 10 by 15. One limit would take value of 0, another will take value of 1, and hence we get this particular answer as 2 by 3 or 0.667. That is, there is 66.7% chance of h being greater than 5 with whatever information we have. So there was a minor typo in this particular integration. Instead of minus 5h, it should be e raised to power minus 5 lambda, because we are integrating with respect to h, because this is conditional given already known lambda. We are interested in probability of h less than 5. This can get quite confusing to some of you, so it may be a good idea to slow it down a bit and understand that given lambda, we only integrate with respect to dh. However, when we have to look into probability of h greater than 5 over all possible values of lambda, it's more like taking a weighted mean, because lambda can take different values and these values will occur with different probabilities. Hence, this particular integration is done with respect to the lambda being a continuous variable. So, if you pay attention to that, this would become quite clearer that when to use integration with respect to lambda and when to use integration with respect to h. Now let us move to more interesting and exciting part, that there was a field, you went there, almost no data existed, you went and met two villagers or locals, they gave you some information that two floods happened. Based on that, you told that probability of flood greater than 5 feet comes out to be 66.7%. That's quite an information, but it starts here, it doesn't end here, because if that is a location of interest, you would like to collect some data and add confidence to your belief, because that particular information was very crude in a sense. So you want to add confidence to your estimates. What you will do, you will go and set up a particular measuring station or a gauge that will record the flood levels, and then try to use prior information to update your understanding about that particular location. So what you did, you set up a gauge there, and then 3 new floods occurred at that particular location over a period of time. And again, we are assuming that all these floods were independent in nature. We recorded these particular floods after some difference so that they are not caused by same phenomena, and that is another way to internalize this concept of independence. So we recorded this maximum elevations of 3 feet, 4 feet and 5 feet in these 3 floods that happened. Now what has been asked is that we have to update the distribution of lambda with this new information that is available to us. Now we will not restart this particular example by discarding what we learned earlier. What we will do is that we want to again derive posterior of lambda given we have observed some new data. We again write it in this form, that in Bayesian we can say that probability of lambda given new data is proportional to probability of new data given lambda into probability of lambda given previous data. Now this is important. What was an uninformed, diffused prior before is now an informed prior. You already included the information from the site and converted your flat prior into a better estimate of lambda. And that should be included as we are bringing in new information into the context. So what we will say that this is proportional to probability of new data given lambda into whatever form we derived earlier, which was 10 into e to the power minus 10 lambda. Also, we know that probability of observing certain height follows exponential distribution separately. That was known to us a priori. So even if new data of flood is being generated, we have no information to change our distribution as of now, because for that we have to observe large number of points and really see that whether my data is actually following that particular distribution or not. But as of now, we have only collected 3 points. So we will not change the prior information about functional form of PDF of h, and we will stick to exponential distribution. So f of h is nothing but an exponential distribution whose functional form or mathematical form is known to us as lambda e to the power minus lambda h. What is the probability of observing h equal to 3? It would be simply lambda e raised to power minus lambda multiplied by 3 or minus 3 lambda. What is probability of h equal to 4? It would be lambda e raised to power minus 4 lambda. Similarly, probability of h equal to 5 would be lambda e raised to power minus 5 lambda. And we have observed all of these. So we can simply say that probability of new data given lambda is equal to lambda e raised to power minus 3 lambda and lambda e raised to power minus 4 lambda and lambda e raised to power minus 5 lambda. Because these particular events are independent, so probability of observing h1 equal to 3 and 4 and 5 can simply be written as their products of individual probabilities, and this simplifies to lambda cube e raised to power minus 12 lambda, 5 plus 4 plus 3, because they are all exponents, I can simply add them, and this becomes our probability of new data given lambda. Now I will assimilate this particular information to update the distribution of lambda in this case, and I will say that probability of lambda given new data is proportional to lambda cube e raised to power minus 12 lambda. This would be multiplied by 10 e raised to power minus 10 lambda, and this simplifies to 10 lambda cube e raised to power minus 22 lambda. Again, I will remove this constant of proportionality with another constant, let us say capital K into 10 lambda cube e raised to power minus 22 lambda. How I would determine this particular value of K? Again, this has to be a valid probability distribution function even after introduction of new data sets. Hence, when I will integrate it in its domain, that is from 0 to infinity, again integration should be equal to 1. Now this integration can be easy or difficult to solve, but if you focus, we have not changed our approach, that how we have been dealing with the Bayesian. Give us data, we will write sign of proportionality, we will add whatever information we know about prior, we remove this constant of proportionality with K, and we validate this particular distribution by integrating it in its domain and equating to 1. And depending upon that, what is the functional form of prior, what is the functional form of likelihood, that integration can be easy or difficult to solve. But in decision making, we have to go towards the decision, and it is a stepping stone for us. We have to get best possible information about associated probabilities. So at this stage, I will not over worry about the complexity of integration, but I will focus on what I am getting out of this particular exercise about the event of interest. So now let us normalize this posterior distribution. We will again write it as 0 to lambda k into 10 to the power 10 into lambda cube e raised to power minus 22 lambda d lambda is equal to 1. What I will do here, I will substitute 22 lambda is equal to u, or lambda is equal to u by 22, and d lambda would be equal to du by 22. Substitution approach that is typically followed in integration of many functions. So not a surprise here, because here you see something of form x into e to the power minus x dx, right? So that would be the easiest way to simplify some of these integrals. So what we will do is that we will again write this after substitution as 10 u cube, because lambda is now u by 22. So 22 cube will come here. K is the constant that we are interested to determine. Instead, I should write capital K because we introduced small k earlier. So this is a different or a new constant of integration, that new normalizing constant that is coming into picture in second case. So this is capital K. This becomes e raised to power minus u. D lambda is du by 22. So this raised to power 3 should become raised to power 4, and I can write this simply as du. Its value should be equal to 1 because this has to be a valid PDF and limits are 0 from infinity. I will take all the constants out, that is k into 10 upon 22 raised to power 4 and integration from u cube e raised to power minus u du equal to 1. Again, as I emphasized, that integration is not my worry. So I will try and find what is the best possible way to integrate these functions. Here is a bit of an advanced concept that I would recommend you to read if you are interested, that this typically represents what we call as gamma function. And its integration, while looks very intimidating, is nothing but it is simply a Greek symbol for tau, tau 4, all constants waiting here into 22 raised to power 4 equal to 1. And this tau 4 takes the value of 3 factorial, k into 10 into 22 raised to power 4 equal to 1. And when I simplify this, k simply turns out to be 22 to the power 4 raised to power 60. Now in this particular question, we were lucky that this resembled this particular gamma function, but that has been one of the biggest limitations of many of these Bayesian approaches in determining posterior distribution, that this particular integral sometimes may not be analytically determined. In this case, this resembled the gamma function, and from understanding of mathematics, we know that integration of type u raised to power t minus 1 e raised to power minus u du can simply be written as tau 4, and tau of t is nothing but it is equal to t minus 1 factorial. And that helped us get into this particular integration. You can also integrate it using UV rule, but you would actually end up at the same point. But here idea is to find the value of k, which in this case comes out to be 22 raised to power 4 into 60. Now that we have determined this particular value of k, we are out of that integration. Because we have determined the value of k, we will substitute that in our original expression and we will go for probability of lambda given new data as 22 raised to power 4 divided by 60 into 10 lambda cube e raised to power minus 22 lambda. This is 22 to the power 4 divided by 6 lambda cube e raised to power minus 22 lambda, where lambda is greater than equal to 0. Now this is our updated posterior of lambda as and when new data is available. Again, if you ask me what is probability of h greater than 5 feet, I will still solve this particular example using identical approach that what we did earlier. I will say that probability of h greater than 5 feet depends on the value of lambda. So this is conditional on lambda, and lambda itself has some probability distribution, p lambda, and it would be integrated for entire domain of lambda, which is 0 to infinity. Now, instead of using the functional form I derived earlier, I will use the most updated form of lambda that encapsulates the information coming from the new data points. And now you can imagine that this particular integration becomes a bit more challenging to calculate, but even if not analytically, I can use some approximation to solve that integral and determine the updated value of probability of h greater than 5 feet. And this process can continue if I have a continuous data stream coming to me, because all I have to do is that again follow the same Bayesian approach and keep on updating the posterior of lambda using earlier available information and treat that information as prior and keep on deriving the new posterior distribution for my variable of interest. And that is how we typically use Bayesian approach in determination of the risks associated, because in this case, certain height of flood is risk for us. Now, over last few modules, we have learned basics of probability and statistics. We also looked into some very simple example, that what are these independent events, how to deal with them, how to give the mathematical treatment to this concept of risk. And we also looked into certain advanced concepts like Bayesian approach for risk determination. Now I think we are fully equipped to go to the discussions on decision analysis using these concepts of probability and statistics, which we will start discussing in the subsequent modules. Thank you.